see. Now what we're going to be seeing is when you're having, let's say I said that this is the direction of magnetic field. This guy was in the plane. Now if the loop starts to rotate, in the clockwise direction that we observed earlier, how things are going to change now. How the things are going to change now. So what we have observed now here is this guy has already started to move. And at some instance, it's going to look like this, isn't it? So we're going to analyze it at that situation when it makes an angle, when the normal to that plane, the normal to the plane of the loop, when the normal to the plane of the loop makes an angle of theta to the B field. With this picture in mind, if I were to compare the scenario in the previous slide with this slide, this theta that you see here, if I want to compare it with this case, you see that that theta is going to be special case of 90 degrees. Yeah. When this theta is 90 degrees, that means B field is like this and my coil is like this, so that the normal to the coil is like this. So it makes an angle of 90 degrees, which is what your previous case would have been. So now that this has started moving, right, you would notice that your forces F2 and F4 are no longer zero. Why so? Because my section 1 is still the same, section 3 is still the same, but section 2 and 4, the angle between the current and the B field is no more 180 degree or 0 degree. Yeah? But does it matter? If you look at the picture, you see that there is a B cross I. There's a B cross I. You would have a force that is going in this direction from the section 4. And for section 2, a force that is going out like this. Going out, this is F4 and this is F2 here. They're pulling, yeah, they're pulling the coil. They are not rotating. They're not going to contribute to the torque. So even though they are no longer zero, it does not matter because the torque is going to be zero. They're not going to cause rotational motion. So what again matters is only F1 and F3 ma. So how about my F1 and F3? Still the same as before. No change in that because the direction of the current has not changed as long as the section 1 and 3 are concerned. In one case it's negative Y and the other case it's positive Y. That hasn't changed. But what has changed is the torque because of that force. Yeah. So if I were to find the torque due to this force that is acting up at this point B, then I need to do my D1 cross F1, isn't it? But my F1 is acting in this direction and this is my D1. If I were to reduce that, my D1 cross F1 will be the same as D1 times F1 sine theta, which is a 90 degree component, a projection of this F1, which makes 90 degree with this D1 vector here. It is all that matters. F2 and F4 have nothing to do with rotation. F2 and F4. F1 and F3 will still cause rotation, yeah? So it is not F1, but a factor of F1 that is going to cause rotation. Because if I decompose F1, right, I can decompose it as perpendicular as well as a parallel component. I can have this one, which is F1 cosine theta ma. Because this angle is theta. This F1 cosine theta is not going to cause rotation. It is the F1 sine theta that is going to cause rotation. Is it important? Not really important, Astor. Not really, yeah. Those are the two forces acting on it, but it won't be able to do any work. It's not important. So you can ignore F2 and F4 altogether. So it is F1 sine theta, the component of F1 that is perpendicular is that matters. This guy is only going to stretch it, so it doesn't matter. Similarly, my F3 is going to be F3 sine theta here and F3 cosine theta, which is F3 sine theta. That is going to matter because this angle is 90°. I want to consider the 90° component there, and that becomes sine theta coming in there. So in general, you get the same expression as before, but with the sine theta in here. So when theta equal to 90, your sine theta equal to 1, which reduces to this guy over here. So the general expression is going to be IA B naught sine theta. And why is it y hat? Because the torque is in the y hat direction. You're spinning in the clockwise direction. So when you are having B field like this, when this guy has come all the way 90° like this, right? There is this theta is going to be 0° ma. When it is 0°, the torque goes to 0, right? The torque goes to 0 because of there's something called as momentum, right? Because of there's something called momentum. There is this angular velocity that is already there since you started off. So it will continue to move even though when there is 0 torque. So the torque is going to be like the sine theta here. At some time instances, it's going to be 0. But whenever it is 0, the momentum that it has here is going to push through it to go to complete the circle. And once it starts over, it's going to have the torque again to turn it around. If I have one current coil, right, just one loop of current, that means one coil of current, that is one loop, then this is the expression. But if I go ahead and loop it up with n turns, yeah, I make this coil with 1, 2, 3, 4, and so on, right? This becomes a coil. It's no more a loop. It has coil. If it has n loops, it's a coil with n loops, then you're going to multiply it by n. So how do you achieve very good torque? You don't want to increase the current. You don't want to increase the magnetic field. Then what you do, you just go and coil more. Then the number of n goes up. The more the number of coils, then more the torque is.